Good morning, or afternoon, or evening, depending on what time zone you're in. So this is another meeting of the Symmetries in Newcastle. It's on April Fool's Days, and as you can tell, we're running that because the main organizer is not actually present because I have COVID, so I'm attending virtually. Everybody else is in, well, not everybody, but most of the people are actually in person in the Lambert Lounge, so I'm missing out on the sandwiches. Anyway, the first speaker of today is our own Max Carter from University of Newcastle, and he was talking about unitary representations of the type 1 property of groups acting on trees. All right, Max.
Thank you, Mikhail. So today I'm talking about unitary representations of groups acting on trees and certain algebras that we can associate to these representations, such as C-star algebras and von Neumann algebras. And I'll be talking a bit about how studying these algebras allows us to understand not only the representation theory of these groups, but also the properties of these groups. And towards the end, I'll talk a bit about some research work I'm working on in this direction. So to start out, I'll give a brief and general overview of the groups I'll be discussing in this talk. And to do that, I need to introduce what the D-regular tree is. So the D-regular tree, which I'll be denoting by TD, is the infinite tree in which every vertex has valency D. And so pictured here is the 3-regular tree. So it's the infinite tree and such that every vertex has degree 3. And here, every path in this tree extends out indefinitely. And so when we have a regular tree like this, we can associate to it a natural notion of boundary. So a point on the boundary of this tree you can identify as kind of the limiting end of an infinite path in this tree. Okay? And whenever we have a boundary point of this tree, which we call the boundary points ends of the tree, whenever we have a fixed boundary point, say omega, it's often useful to think of draw the tree in this formation here, where we identify an infinite path extending out to this end omega of our tree, and we draw the other vertices of the tree in below this infinite path. So these are the D-regular trees. And in this talk, I'm interested in automorphism groups of D-regular trees and their representation theory. So whenever we have a connected locally finite graph, then the automorphism group of this graph, when it's grouped with the topology of uniform convergence on compact sets, is a totally disconnected locally compact group. And I'll abbreviate that as TDLC group for the remainder of this talk. And prototypical examples of such groups are when we have the automorphism group of a D-regular tree. And from a representation theoretic perspective, there's kind of two classes of interesting subgroups of the automorphism group of a D-regular tree. So there's the boundary, the automorphism groups that act transitively on the boundary of that tree, and the automorphism groups that don't act transitively on the boundary. So amongst the boundary transitive groups, generally ones that act transitively on the vertices in the boundary and sometimes satisfy other group theoretic properties, such as property P, of interest, both from group theoretic and representation theoretic perspectives. Don't worry if you don't know what property P is. And then on the non-boundary transitive side of the spectrum, there's groups such as groups that stabilize the horocycles of a boundary point omega. And so a group that stabilizes horocycles of a boundary point of an end omega are groups that, such that every automorphism in that group fixes the end omega and also fixes another vertex in the tree. And whenever an automorphism fixes an end and the vertex, it always fixes the infinite path between that vertex and the end we're fixing. And examples of such groups are, for instance, the p-adic rationals or the formal Laurent series over a finite field. And these act on a tree by Basset theory. Or we can also have stabilizers of horocycles of an end, and we can, for instance, kind of add a translation to these groups. So we have groups that stabilize the horocycles of an end, and then we add a translation, so we can kind of slide the graph this way, and also do automorphisms on a tree that fix the vertex and the path between the end, and combinations of the two. And having a translation to these groups basically amounts to taking a semi-direct product with the integers. And I'll be talking about groups in this form a bit later in the talk. So these are the automorphism groups I'll be discussing in today's talk. And now I want to say a bit about representation theory. And I want to assume that anyone knows much about representation theory of like compact groups, so I'll spend a bit of time on this. Now, I'm interested in the unitary representation theory of locally compact groups. So a unitary representation of a topological group G is a pair where we have a homomorphism pi and a Hilbert space H pi, and pi is a homomorphism of our group into the group of unitary operators on our Hilbert space H pi. And it also has to satisfy a continuity property that for every vector in our Hilbert space, the map that sends a group element G to pi G psi is continuous with respect to the group topology on G and the norm topology on our Hilbert space. And this Hilbert space can have arbitrary dimension, and it can have uncountable dimension. But for instance, when our group is set countable or separable, we can assume that the Hilbert space has at most separable dimension. Sorry, at most countable dimension. And a prototypical example of a unitary representation of a locally compact group is when we have the left regular representation. So when we have a locally compact group G, every locally compact group has a Haar measure, and so we can integrate functions in that group. So it makes sense to talk about, say, the algebra of square integrated functions in our group G. And for every element X in our group, we can define a unitary operator on L2 of our group that just acts by left translation on square integrable functions. And the homomorphism that sends an element of our group G into the unitary operator Lx is a unitary representation of group G. And so this works for any locally compact group. Now, I just want to give a few definitions that I'll use throughout my talk, and go and get into some examples and other information. So, whenever we have a unitary representation of a locally compact group, we call a subspace of the Hilbert space H pi G invariant if the subspace is invariant under the action of our representation. And whenever we have a closed G invariant subspace of our Hilbert space, then the representation decomposes as a direct sum of sub-representations, we call them. So we can decompose our representation into simpler representations and study these simpler representations instead to understand our representation pi. And this motivates the definition of irreducibility. So we call a unitary representation irreducible if there does not exist any closed G-invariant subspaces in our Hilbert space. And the other definition I want to give is unitary equivalence. So we call two representations, say pi and sigma, on their respective Hilbert spaces. We call them unitary equivalent if there exists a unitary operator between the corresponding Hilbert spaces that conjugates one representation into the other. So this is the definition of unitary equivalence. And then using these two definitions, we can define what we call the unitary dual of our group G. And the unitary dual is the set of all irreducible the set of all equivalence classes of irreducible representations under unitary equivalence. And we usually identify an equivalence class in the set with just a representative of the equivalence class. So we usually talk about the unitary dual as just the set of irreducible unitary representations after equivalence. And so when G is a locally compact abelian group, all its irreducible unitary representations are one-dimensional. So they act on a copy of the complex numbers. And in particular, because they're unitary, they are just homomorphisms of our group into the torus, continuous homomorphisms into the torus. And we call such homomorphisms characters of our group. And so in this case, for a locally compact abelian group, the unitary dual is itself a locally compact abelian group. And also the unitary dual of the unitary dual is isomorphic to the group we started with. So in some sense, the irreducible unitary representations kind of preserve all information about our group. But in general, for non-abelian locally compact groups, the unitary dual does not have a group structure, but we can equip it with a topology called the Feld topology and a sigma algebra structure called the Mackey-Burrell structure. And this sigma algebra is not necessarily the sigma algebra of the Feld topology. And this topology in the sigma algebra, understanding that gives us information about the irreducible unitary representations of our group G.
Can I ask a quick question?
Yeah.
The Mackey-Burrell structure, so is that not the one that comes from the Feld topology? Is it a different one?
Well, it's equal to the Burrell sigma algebra from the Feld topology, if and only if the group's type 1. Okay. I might mention that a bit later. And just while I'm on this slide still, I'll mention that what I say here about the unitary dual of the unitary dual being isomorphic to the group itself, that's quite a famous piece of work called contrariety. And I'll just give a few examples, partially to motivate what I'm going to say next. So in the case of when we have the locally compact abelian group, the torus, then we get a character from each integer n, which just, that corresponding character from integer n is just the continuous homomorphism of the torus that maps a complex number z to its nth power. And it turns out that the unitary dual of the torus is precisely just this set of characters in bijection of the integers. And this is isomorphic as a locally compact abelian group to the integers. And maybe as a consequence of stuff you've seen in Fourier analysis, these characters form a orthonormal basis of L2 of the torus. And if you haven't seen this result, then you can maybe motivate it by the Fourier series of an L2 function. And each of the subspaces spanned by the individual characters is invariant under the action of the left regular representation of the torus. And so, as a result, the left regular representation of the torus decomposes as a direct sum of irreducible representations acting on each of the subspaces spanned by our characters. So this gives a decomposition of the left rectangle representation of the torus into irreducible one-dimensional representations.
Yeah, so Max Kn is one-dimensional.
Yes.
We don't really explosion into a one-dimensional space.
Not really. Yeah. So in particular, when we have the left radial representation of the torus decomposes as a direct sum of irreducibles. But in the case of when we go to a non-compact, locally compact abelian group, for instance R, then the irreducible unitary representations are still characters of that group. And in the case of R, the characters are in one-to-one correspondence with the elements of R. But we don't have a direct sum decomposition of the left radical representation. By the same argument as on the previous slide. And you could motivate this, for instance, by looking at the Fourier inversion formula for an L2 function on R. In this case, the Fourier inversion formula decomposes an L2 function, but it's a continuous decomposition of the L2 function over the unitary dual of R in this case. And this motivates the following two results. So it's a famous theorem called the Peter-Fowl theorem that every representation of a compact group decomposes as a direct sum of irreducible unitary representations of that compact group. And it's unique up to, decomposition is unique up to unitary equivalence. And in some sense, the proof of this is basically analogous to what I said about the decomposition of the left radical representation on the torus. But in the case of non-compact groups, we cannot always just consider decompositions of unitary representations into direct sums of irreducibles. We have to consider, well, for groups that are locally compact, separable and satisfy a property called the type 1 property, every unitary representation decomposes into what we call a direct integral of irreducible unitary representations, and it's unique up to unitary equivalence. So for compact groups and locally compact separable type 1 groups, we can always reduce the study of general unitary representations to solely understanding irreducible unitary representations and understanding the unitary dual of our group. But when our group does not satisfy this type 1 property, then we can no longer reduce the study of general unitary representations down to studying solely irreducible unitary representations. So for type 1 groups, for non-type 1 groups, it's quite difficult to understand the unitary representations because we can no longer reduce it down to studying irreducibles, but it's often quite feasible to classify the unitary representations in general for type 1 groups. And don't worry if you don't know what a direct integral is. It's not going to matter for the rest of it at all. I'm just motivating some things. And now I'll say a bit about this type 1 property and say what it is and some aspects of it. Now, whenever we have a locally compact group G and a unitary representation of G, we can always extend our unitary representation pi to a representation of the algebra L1G. And we usually just identify the representation of the group with the corresponding representation of the algebra L1G. And this extension of our representation is defined by this integral. So pi of an L1 function f acts on a vector psi of our Hilbert space by just computing this integral here as a vector space scaling integral. And so this gives us an extension of our representation to a representation of the algebra L1G. And this is also a algebra homomorphism of L1G that also preserves the adjoint operation on this algebra. And so as a result, we get a pi of L1G is a sub-algebra of the algebra of bounded operators on the Hilbert space H pi. And it's also closed under the adjoint operation on this in the space of bounded operators on this Hilbert space. So we call this a star algebra because it's an algebra and it's also closed under this adjoint operation. And from here there's two natural algebras that we can define. So pi of L1G is this star algebra on the Hilbert space H pi, and we can take the closure of this algebra, for instance, in the norm topology, in the operator norm on the space of the bounded operators, or we can take the closure in the strong operator topology, which is just the topology of pointwise convergence on the bounded operators on the Hilbert space. And so we get a norm-closed star algebra and a star algebra that's closed in the strong operator topology. And norm-closed star algebras on a Hilbert space are called C-star algebras, and star algebras closed in the strong operator topology are called von Neumann algebras. And a particular example of such algebras that's important to the study of the representation theory of locally compact groups is the group C-star algebra. So if we define a representation plane max to be the direct sum of all what we call cyclic unitary representations of a group G, don't worry if you don't know what cyclic representations are. Then in some sense, this representation kind of contains all representations of that group. So the C-star algebra corresponding to this representation pi max, in some sense contains all information about the unitary representation theory about group G. And we call this algebra the group C-star algebra about group G and denote it like this. And just being a bit more specific, so the unitary representations of our group G are in one-to-one correspondence with non-degenerate star representations of this C-star algebra. So by star representation, I mean a homomorphism of the C-star algebra into the bounded operators on some Hilbert space that also preserves the adjoint operation. So these are C-star algebras and von Neumann algebras associated to representation pi. And let me say a few words about C-star algebras and von Neumann algebras briefly. So amongst these C-star algebras, from a representation theoretic perspective, there's kind of two or three important classes of C-star algebras. So there's the CCR C-star algebras, the GCR C-star algebras, and then kind of all the C-star algebras that don't fit into these two classes. So a CCR C-star algebra is a C-star algebra such that for every element F in our algebra and every irreducible star representation of our algebra, the image pi f is a compact operator. And by a compact operator is an operator that can be approximated by operators acting on finite dimensional, by operators that have finite dimensional range. And so the CCR algebras are just the CCR C-star algebras are ones and such that the image under every irreducible star representation is contained in the compact operators on that Hilbert space. Those are the CCR C-star algebras. And then the GCR C-star algebras are those that have a composition series of closed two-sided ideals, such that each of the corresponding quotients of the composition series is CCR C-star algebras. But here alpha can be some arbitrary ordinal, so this composition series doesn't necessarily have to be final. But it's the case for GCR C-star algebras that under every irreducible star representation, the image contains the compact operators in that Hilbert space. So CCR C-star algebras are those that act by compact operators, and GCR ones are ones whose action contains the compact operators. And I'll just note that C-star algebras that are either GCR or CCR have very nice representation theory, and in general we can understand the representation theory of these algebras quite well. But for C-star algebras that don't fit into these classes, then their representation theory is quite poor, and in general we can't say a lot about the representation theory of algebras that don't like C-star algebras that don't like these classes.
Sorry, hang on. How did you say the second thing followed, that for a GCR it contains the compact operators?
That's not obvious.
That's not.
Yeah, don't worry about the proof of that. I'm just noting that. Now on the other side of the picture for von Neumann algebras, every von Neumann algebra contains a large amount of projections, and it's the case that every von Neumann algebra, the linear span of its projections is norm dense in the von Neumann algebra. So understanding the projections of the von Neumann algebra allows us, in general, to understand the structure and properties of the corresponding von Neumann algebra. And by studying the projections of a given von Neumann algebra, we can classify von Neumann algebras into three different types: the type 1, type 2, and type 3 von Neumann algebras. And here in the brackets, I've given the description of the types for factor von Neumann algebras, which are kind of the building blocks of general von Neumann algebras. And I'll note that the projections of the von Neumann algebra form a complete lattice. So that's what you can go to minimal from, you can take the definition of minimal to just be minimal in this lattice, but I won't say what a finite projection is, because it doesn't matter for what I'm going to say in the present. And now, type 1 von Neumann algebras are just up to isomorphism, direct sums of tensor products of abelian von Neumann algebras and the algebra of bounded operators on some Hilbert space. So in general, these are quite easy to understand. Well, they're quite well understood as abelian von Neumann algebras, and the algebras of algebra of bounded operators on a Hilbert space is a quite, in general, quite well understood algebras. But on the other hand, type 2 and type 3 von Neumann algebras are very complex, and it's a large area of study trying to understand the properties, the structural properties of type 2 and type 3 von Neumann algebras. And I'll note that the factor von Neumann algebras, which are the building blocks of all von Neumann algebras, type 1 factors are just isomorphic to BH, the bounded operators in some Hilbert space. Now, so when we have a unitary representation of a local compact group G, then we call that representation type 1 if the von Neumann algebra that this representation generates is a type 1 von Neumann algebra. And we say that the group is type 1 if every unitary representation of the group is a type 1 representation. And it's a famous theorem by Lim from the 60s that a group being type 1 is equivalent to a lot of other properties about the representation theory of that group. So for instance, the group being type 1 is equivalent to the group C star algebra of the group being GCR. It's equivalent to the image of L1G of every irreducible unitary representation containing the compacts. It's also equivalent to a lot of other properties about the Mackey-Burrell structure and Feld topology on our unitary dual. And in the case when G is not type 1, and these properties about the unitary dual don't hold, it ends up being quite hard and sometimes infeasible to try and describe the unitary dual of the group G. So we get this strong dichotomy between type 1 locally compact groups whose unitary representation theory is in general quite easy to work with, but was in general reasonably well understood, and non-type 1 groups whose unitary representation theory is quite difficult to work with, and we can't usually classify all the unitary representations of such groups. Now I'll talk a little bit about the unitary representation theory of groups act on trees and some work I'm doing at the moment. And I'll say a bit about past research on the unitary representation theory of tree automorphism groups. So it's a quite well-known theorem by Nebbia from the 90s that for group automorphism groups of trees that are closed, unimodular, and vertex transitive, the group C star algebra of that group being CCR implies that the group acts transitively on the boundary of our tree. And it was also conjectured in the same paper that if we have a unimodular group that's vertex and boundary transitive, then the group has to have CCR group C star algebra. But this conjecture is still open, and there's work going towards trying to understand this, and this conjecture has been verified for quite a large collection of groups acting on trees. And for instance, it was recently verified that the groups classified by Inflow-Radu satisfy this conjecture. So this gives a seemingly strong correspondence between properties of our group C star algebra and properties of our automorphism group G on a tree. And in more recent work, in a paper by Lydia and Rao, it was posed as a problem that, although the problem was posed a bit more specifically than this one, was summarizing it here for brevity, that for closed non-amenable groups of automorphisms of a regular tree that act minimally on the tree, meaning that the group doesn't fix any proper non-empty subtree of our tree, that the group being type 1 is equivalent to it acting transitively on the boundary of our tree. And there's still, this problem is still open in general, but it has been checked in many cases, both in this paper where they posed the problem, and also more recently, this result by Contrast, Lanto, and Mano, that shows that any closed non-amenable group of automorphisms of a regular tree that are minimally on a tree, then the group being type 1 implies that it acts too transitively on the boundary. So there's also this strong correspondence between the grouping, the automorphism group of a tree being type 1 and the group acting transitively on the action of the group on the boundary. Now, I'll say a bit about research. For the remainder of the talk, I'll talk a bit about research I'm doing at the moment. And research work I'm doing at the moment is concentrating on these style groups, which which is a class of groups that don't fit into any of the categories, any of the classes of groups on this slide, as these star groups are amenable and non-unimodular. So this studying the representation theory of these groups to give interesting alternative examples of the representation theory of groups like entries compared to the groups that are of interest in the results of that previous slide. So by a scale group, I mean it's a group of automorphisms of a regular tree that's closed in the topology on this automorphism group, and they act transitively on the vertices of our tree, of the deregular tree, and they fix some fixed end omega of our tree. And I won't say too much about the structure of star groups in general, but for instance, every star group is a semidirect product of the subgroup of elliptic automorphisms in our star group, and a subgroup generated by a translation that shifts the tree towards our end omega. So the elliptic subgroup is precisely the subgroup of all elliptic automorphisms, and the elliptic automorphisms are those that fix some vertex in our tree, and hence fix the path from that vertex all the way out to the end omega. And then this translation is just shifting the tree towards or from the end omega. Now, examples of star groups include, for instance, if we just take all the automorphisms of our tree that fix some end omega, that's the largest star group we have. But other non-obvious examples are, for instance, the p-adic rational semidirect with Z and the formal Laurent series of semidirect with Z that I mentioned earlier in the talk. And the Z actions here are given by multiplication by P and multiplication by T. And the fact that these star groups follows from either Basset theory or also a more general theorem about TDLC groups called the tree representation theorem, which says that certain groups satisfying certain properties which we satisfy act on a regular tree as a star group. And also this tree representation theorem also says that every non-unistable TDLC group has a sub-quotient isomorphic to a star group. So star groups are fairly fundamental from the perspective of general TDLC groups. Now, I want to give a few other examples of star groups that I'm looking at the moment. And to do that, I need to define what a contraction group is. So by contraction group, I mean a topological group G paired with an automorphism alpha of our group, such that for every element X in our group, powers of alpha applied to X converge to the identity. This is a contraction group. So for instance, the p-adic rationals paired with the automorphism that is multiplication by P, this is a contraction group. And also, if we have the restricted direct product of copies of a finite group, and the automorphism is the right shift on sequences in this group, then this is also a contraction group. And it follows from the same, the tree representation theorem I mentioned just before, that if we have a totally disconnected, locally compact contraction group, then when we take the corresponding semidirect products with the integers, this is a star group. And where the Z action on G is just given by applying powers of alpha to elements of G. So we get a large class of star groups from studying contraction groups. And I'm currently interested in the representation theory of groups arising this way. And let me say a bit about the structure of contraction groups. So in a paper by my supervisor George Willis and Public Law, it was shown that every TDLC contraction group is a unique direct product of p-adic Lie groups, a unique finite direct product of p-adic Lie groups, and the subgroup of torsion elements in our group G. And now, from a representation theoretic perspective, the p-adic Lie groups have been, in general, their representation theory has been fairly heavily studied, and questions about their representation theory are usually generally quite challenging to understand and solve. However, the torsion ones, the representation theory of this component is, in general, hasn't been studied as much, and I'm mainly concentrating on understanding the representation theory of Stauer groups whose elliptic subgroup is a torsion locally compact contraction. Now, in the case when we have an abelian TDLC contraction group, and this theorem, we can say exactly what these groups are. And I'll tell you what they are here. So if we let omega p denote a set of irreducible monic polynomials in QP adjoint X that have roots in some algebraic closure of QP with norm less than 1, strictly less than 1, then we can define these groups that are quotient of QPX by F times QPX. And we can also equip these groups with an automorphism, which we denote by alpha X, which is a multiplication by the coset X plus F QPX. Okay? And these groups, it turns out that these groups are contraction groups, although well, it's not completely obvious why that would be. And a theorem in the same paper by Willis and Blockner, it was shown that every TDLC abelian contraction group is a direct sum of finitely many copies of groups of this form EF, and also finitely many copies of a restricted direct product of cyclic groups of prime power order. And the corresponding contractive automorphism for these groups is precisely just acting on the factors EF by the corresponding automorphism for these groups EF and the right shift for the corresponding restricted direct products. So these are the TDLC abelian contraction groups. Now I've proved the following results about the representation theory of the associated Stauer groups. Now if we let this set here omega subscript 0p be all the polynomials of the form xn minus a when some integer a is an element of qp, then if we have we define a group n to be to be a direct sum of finitely many copies of EF arising from polynomials of this form, and a direct sum of some finitely many copies of restricted direct products of cyclic groups of prime power order, then the corresponding Stauer group, well, I can say that the group C star algebra of this group is GCR, but it's not a CCR, C-star algebra. And also, I'm classifying the unitary dual of this group. So in particular, if we have the orbits of Z acting on the unitary dual of N. So this group N is an abelian group, and its unitary dual is some group of characters of this group. And Z acts on the unitary dual by conjugation of characters. And if we pick a cross-section X of these, of the orbits of this action, then the unitary dual is precisely, we get all the characters of Z which act trivially on the normal subgroup N, and this is the unitary dual of Z is precisely just the torus. And we also get all these representations which we call induced representations of characters from this normal subgroup N. This is the unitary dual of these scale groups. And let me just say what these induced representations are. So, induction of representations is a general process that allows us to, if we're given a representation of some subgroup of our group, we can induce it to a representation of the whole group. And so in general, if we have a group G and an open subgroup H of our group G, and a representation pi of H, then the induced representation of pi from H to G acts on the Hilbert space L2 of G by H. And in the example we've got here with these scale groups, the induced representation of these characters from our normal subgroup N to the scale group is precisely acts on L2 of Z by what we do this it acts on a function psi L2Z by we do this shift of the function and then we scale by this complex number that's defined by our character psi. So this is the action of the induced representations on L2Z. And this gives, and in particular, this result gives an uncountable class of scale groups that are type 1, and for which we know they're irreducible unitary representations. I'll just comment briefly on the proof of this result. So the group C star algebras of these scale groups are isomorphic to what we call a cross-product C star algebra. And by fairly advanced cross-product C star algebra theory, it turns out to be the case that the C star algebra is GCR if and only if the Z orbits, the Z orbits of the action of Z on the unitary dual of N are locally closed, and the C star algebra is CCR if and only if all the orbits are closed. And to determine the irreducible unitary representations of these groups, I use what is called the Mackey machine, which is a general process that allows us to, when given a group and a normal subgroup, we can, by studying the irreducible unitary representations of the normal subgroup and the action of our group on the irreducible unitary representations of the normal subgroup, the Mackey machine allows us to reconstruct all the irreducible unitary representations of the larger group from the irreducible unitary representations of the normal subgroup. And this is a general process that works for a large class of groups under fairly general assumptions, but is reasonably simple here as we understand our problem. Now, it turns out to be the case, though, that not all scalar groups are type 1. So it was shown in a result in a paper by Capras and Monod just late last year that scalar groups of this form, where the elliptic subgroup is a restricted direct product of finite single abelian groups, and the corresponding standard groups are not type 1. So we have type 1, and we have classes of type 1 standard groups and classes of non-type 1 standard groups. Now, the general problem that I'm working towards solving is the following. So, actually, let me just backtrack a little bit. When I was talking about the Mackey machine, I said by studying the unitary representations of the normal subgroup, we can reconstruct the representations of the whole group. But one of the conditions for Mackey analysis to apply is that the normal subgroup has to be type 1. And so I want to work towards determining which Style groups arising from torsion TDLC contraction groups are type 1. And to do so, we need to determine which torsion locally compound contraction groups are type 1. And in the case where they are type 1, we need to determine their irreducible unitary representation. So that's the general problem I'm working towards solving. Understanding the representation theory and the type 1 property for torsion TDLC contraction groups, and also about the corresponding Style groups. And the next intermediate question is to work out this problem for when the elliptic subgroup is a two-step nilpotent torsion locally compact group. And the two-step nilpotent torsion TDLC groups are precisely of this form, where we have a central extension of the formal Laurent series over a finite field by itself. And these extensions are defined by certain 2 co-cycles. And I haven't started working on this problem yet, but we can also apply a Mackey analysis, the Mackey machine here, to understand the representation theory, the representations of this group, as we have this normal subgroup formal Laurent series, which is type 1. And we can then work on inducing representations from this normal subgroup, the whole group. But I haven't quite started working on this yet. So this is the next step. Now that's all I've prepared for today. So in the talk here, and we can have some questions now if there are.
Okay, are there any questions for Max?
I'll ask you a question. I was just writing down a note about the last slide. No, the last slide.
Which one, sir?
The last slide, the slide you were on. Did you say this was a nilpotent group? Did you use the word nilpotent?
Two-step nilpotent.
Yeah.
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 For this one here.
Yeah.
Yeah. Does that answer your question?
That was the question, yeah.
So any other questions?
Perhaps you could say something about the non-torsion case. What's the case?
Sorry?
The non-torsion case, because the groups there are all the
Well, understanding the non-torsion case, then you're going to be looking at PA groups. And, well, in general, I don't think it's understood which PA groups are type 1 and not type 1. So, for instance, unipotent PA groups have to be type 1. So, we could study the unitary representation theory of scale groups arising from such groups, but in general, it's not understood which PA groups are type 1 and not type 1.
Right, but what about the contraction groups?
Yeah, I mean, PA groups are contraction groups.
Right.
Well, in general, I'm not even sure what groups lie in this class. P-adic B groups are contraction groups. But understanding the representation theory of P-adic B groups is a question that's not completely well understood in general.
Okay. Any other questions? Well, it seems that there are no further questions, so let's thank Max again. And I believe it's time for a lunch break, so we'll meet again in 90 minutes.